All right, so question number 18. In this question, we basically have a cube, uh, and each vertex of the cube is labeled from 1 through 8. And we want to use each integer exactly once, such that the sum of the four numbers on each, like sum of the four numbers on the vertices of each face is the same. And we want to find how many different arrangements that are there where rotations are considered the same. Okay, so for this question, basically, what you want to do is, so you have your cube. So the first observation you kind of have to make is like, let's first try to find like the sum of like all the numbers. Like let's try to find what is the, because it said, the question says that the sum of the four numbers on the vertices of a face is the same for each face. So let's first try to find what is this same value? Like, what is this common value? Can we find that? Well, notice that if we were to add all of the numbers on all of the faces, like for example, this vertex here, it would be counted exactly 3 times, right? It would be counted one time when you count the sum for this face. It'd be counted another time for when you count the sum for this face, and it would be counted one more time when you count the sum for this face. So each vertex is going to be counted 3 times in the total sum. And since the numbers are 1 through 8, the total sum, like if you were to add up the 4 numbers on the top face, add up the 4 numbers on the bottom face, add up the 4 numbers on like every single face, the total sum you would get is 3 times 1 plus 2 plus 3 plus ... plus 8. And then since there are 6 faces in a cube, you would divide by 6 to find what is this common sum. And it turns out for this, you would get a value of 18. So that tells us that each face of the cube has a sum of 18. Basically now what we want to do is we kind of want to like, so we have our cube. So let's consider where is the vertex labeled 1, right? Let's just assume that like the 1 is on that vertex. It really doesn't matter, right? Because like, for example, if the 1 was over here, then we can just like simply rotate the cube so that like the 1 comes over here. So like without loss of generality, assume that the 1 is on this vertex. So now what we can do is let's assume that these 3 vertices that are adjacent to the 1, right? So like, I'll do it in blue. It's like this one, and this one, the 3 vertices that are like adjacent to the vertex labeled 1. Let's call them X, Y, and Z. And since we just found out that like the sum of the numbers on each face is going to be 18, that tells us, for example, that this number here is going to be 17 minus Y minus Z. This point here is going to be 17 minus X minus Z. And this one here is going to be 17 minus X minus Y, right? That's just because the sum of each face has to be 18. So yeah, and then this vertex here, like, since this like face must add up to 18, then that tells us if you add up these, if we call this like, I don't know, W, right? Then we have Y plus 17 minus X minus Y plus 17 minus Y minus Z plus W, that has to equal 18. And it turns out you can cancel off a Y like that. And it turns out W is going to equal X plus Y plus Z minus 16. All right, so we can replace W with X plus Y plus Z minus 16. All right, okay, so now the next observation we have to make is, the question mentioned how we have to use each number exactly once, right? So since we've already used the 1, we can't use the 1 again. So that means this number here cannot be 1. Like, that might seem like obvious, but like, this is pretty important in solving the question. So basically, clearly X plus Y plus Z must be greater than 16, right? Because if x plus y plus z was like 16 or less, then this would be like 0. Then x plus y plus z minus 16 would be 0 or less. But we can't have a number that's 0 or less. All the numbers are at least 1. But we can actually say that x plus y plus z has to be greater than 17. And the reason is because if x plus y plus z was 17, then x plus y plus z minus 16 would be 1, but we can't use 1 again. So that's why we have like this kind of that restriction now. Okay, so we know that x plus y plus z is greater than 17. I can also write this as x plus y plus z is greater than or equal to 18, right? It's like the same thing. I'm just kind of rewriting it in a different way. So we know that the possible vertices are 1, 2, 3, 4, 5, 6, 7, 8, right? So it turns out there's actually very like few, there are very few number of possibilities on what x, y, and z can be, assuming that order doesn't matter. We'll talk about order later. So notice that like, if we can kind of do like some simple casework, right? If x plus y plus z, since we know it's at least 18, we can do casework on what the value of x plus y plus z is. So if x plus y plus z is equal to 18, then it turns out we have, we can have x, y, z. This can equal 3, 7, 8, 4, 6, 8. And yeah, or we can also have 5, 6, 7. And yeah, those are only 3 possibilities if x plus y plus z is equal to 18, right? So let's and then let's just continue listing out all the cases, and then we'll check each one by one. If x plus y plus z is equal to 19, then it tells us x, y, z. That can equal, then x, y, z can equal 4, 7, 8. It can equal 5, 6, 8. And yeah, those are all the possibilities when x plus y plus z is equal to 19. We can also have x plus y plus z equals 20, right? And in that case, you can have x, y, z equals, you can have 5, 7, 8. That's the only possibility. And the final case is x plus y plus z is 21. And the reason this is the final case is because the maximum possible value of x plus y plus z is when the values are 6, 7, 8, because those are the largest possible values, 6, 7, 8. So those are our possibilities for what x, y, and z can be. And now we can check which one of these work, right? So let's first look at 3, 7, 8, right? 3, 7, 8. Let's first like evaluate and see if this one works. If x equals 3, y equals 7, z equals 8, that's for, okay, so we're talking about this case right now, right? The reason this case won't work is because like if you put x equals 3, y equals 7 into here, right? Then 17 minus x minus y is going to be 17 minus 3 minus 7, which is 7. So this is going to be equal to 7. But like if this value is going to be 7, right? Like if this value is 7, but y is also 7, that means you've used the same number twice, and you can't do that, which is why 3, 7, 8 does not work. Now let's move on to the case for 4, 6, 8. 4, 6, 8. Let's check if this one works. So it turns out this one does work. So I'll briefly show like why it works. So, all right. So in this case, we have x equals 4, y equals 6, z equals 8. Then like, notice that like x here, you would have 4, y is 6, z is 8. 17 minus y minus z, that's going to be 3. 17 minus x minus z, that's 17 minus 4 minus 8. This is going to be 5. So this one's 5 over here. And x plus y plus z minus 16, that's going to be 4 plus 6 plus 8 minus 16, which is 2. And this top vertex here, 17 minus x minus y is 7. So it might seem kind of messy, but like notice that we have the number 1, 2, 3, 4, 5, 6, 7, 8. Each time it's used exactly one time, which is why this case does work. So like this case works. All right. It turns out you can like quickly like check a lot of these, and you can continue checking, and it turns out like 5, 6, 7, it turns out doesn't work. It turns out there's not that many that actually work. 4, 7, 8 works, and 6, 7, 8 works. And it turns out these don't work. You can do like the similar reasoning where you notice that like 2 of the vertices have the same value, which is like a contradiction. So it turns out we only have 3 possible values, 3 possible pairs. We have this one, and this one. But like we're almost done, but we're not exactly done, because we kind of have to be careful, right? Because if we have like a cube, right? Like for example, let's take the case where we had 4, 6, 8, right? That's one of them that worked. Notice that like so you have your 1 here, you have 4, you have 6. Oops, 6 not supposed to go there. And then you have 6, and then you have 8. Notice that like if you replace this, so let's keep the 4 there. If you replace the 6 with an 8 and replace the 8 with a 6, it turns out like this will give a different configuration of the cube, right? You can't like, it's not possible to like rotate this cube to make it like the same as like 4, 8, 6. But like this gives the same result because it's kind of like symmetric, right? By the same logic, you would have like that 4, 8. So if 4, 6, 8 works, then that tells us 4, 8 or 4, 6, 8 works, and 4, 8, 6 also works. And the interesting thing is that like if you look at the black numbers, like you can't rotate them so that they exactly match the red numbers. So this actually gives another configuration possibility. And since we have 3 of these, we have 4, 6, 8, 4, 7, 8, and 6, 7, 8. That's 3 possibilities. And for each one, there are 2 ways to like kind of generate a new triple. So you would do 3 times 2, and you would get 6 as your final answer.